Okay, hi. This is my video number 25. Yeah, my video number 25. So now I'll talk in this video. I'll talk on the conversion of differential equation into an integral equation. Yeah. Conversion of differential equation into differential equation into integral equation. Now, as we know that it's not that focused. Okay, as we know that in solving the ordinary differential equation as well as solving the partial differential equation, we often arrive at solving the integral equation. Yeah. For example, if you use a Laplace transform, right, or if you integrate the differential equation, you will end up at the differential equation, integral equation. Excuse me. So the same thing, we can solve the differential equation into using the differential equation by conversion into the integral equation. All right. So for example, for the beginning, let's for the how do we reckon between initial value problem and boundary value problem? Yeah. For the initial value problem, yeah, we have initial value problem. What is the difference between these things? Yeah. Initial value problem. So for example, we have t2y 2x dx squared plus y equal to x, with the condition that we have y0 equal to 2 and y prime 0 equal to 3. So in this case, we can see that this condition involving the dependent variable and its derivative, yeah, dependent variable which is y and its derivative, whereas we fix the independent variable. Yeah, in this case the independent variable is 0, whereas the one that change is that the dependent variable which is y and y prime. As well as if we have other example that we have here, del d2y dx squared plus y equal to x, with condition say y1 equal to 2 and y prime 1 equal to 2. So again, if you look at this in this example, that the the one that changes is the dependent variable y and y prime, whereas for the independent variable which is x, we fix at 1. We have x when x equal to 1, we have y 2 when x equal to 1, y prime is 2. Is 2. And then the other one is the boundary value problem. Yeah, the boundary value problem the example is that if you have say t2y to dx squared plus y equal to 0, with the condition that ya equal to y1, yb equal to y2. So here in this case we can see the one that changes is the independent variable. You see, x from a, xa and x equal to b, whereas the dependent variable we fix that y, and the second condition also we use y at the different two different point, you see. So in this case we call this is as a boundary value problem. Now let's see how do we convert the initial value problem, which is the first case here, into Volterra integral equation. Yeah. Conversion of I put initial value problem i.v.p. into Volterra integral equation, into Volterra integral equation. Okay. Now we consider the initial value problem. Consider the initial value problem given by general initial value problem. We have dny dxn plus c1x dn minus 1y dxn minus 1 plus c2x dn minus 2y dxn minus 2, and so on, cn minus 1 x dy dx plus, we don't have space there, plus cn x y equal to phi x. Let's call this equation number 1. With the condition that we have y a equal to a naught, y prime a equal to a1, and y double prime a equal to a2, and so on. Y n minus 1 a equal to a n minus 1. Okay, let's call this as a equation number 2. I need one more here. So plus that, say y n minus 2 a equal to a n minus 2. Okay, so where the function c1x, c2x, cnx, and phi x itself are continuous, in the interval in, say, x, a, and b. Okay, so in order to convert that integral, so we introduce the unknown function g, introduce the unknown function g x such that dny dxn that equal to gx. Okay, so let's call this equation number 3. Now if we integrate both sides of this integral of this equation, now integrate with respect to x, with respect to x from a to x, from a to x, So we got, so integrate this from a to x though. So what we have is that the n minus 1 y dx n minus 1, we evaluate x from a to x. On the right side we have integrate gx a to x dx. Okay, and substituting this the limit, so we got d n minus 1 y dx n minus 1 minus we have y n minus 1 a. This is equal to, right hand side we have integrate a to x gx dx. Okay, and then if we use the condition number 2, that condition here where I use the that condition, the last one, okay, using condition 2, I take the last one, this one here. All right, so we have y n minus 1 a equal to a minus 1. So we use this that and we substitute into this equation here. So what we have, dn minus 1 y dx n minus 1, this equal to, bring it to the right side, integrate a to b gx dx plus a n minus 1. Okay, and then of course here in this case you can just change the variable, all right, or we can write this dn minus 1 y dx n minus 1 is equal to integrate a to sorry, this a to x, sorry, this is a to x, we have gt dt plus a n minus 1. Okay, so let's call this equation 4. Now again, if you integrate this equation 4, so what we have, integrate, I just write like this, integrate 4 from a to x with respect to x. So what we have, dn minus 2 y dx n minus 1, we evaluate from a to x, then we have this equal to integrate a to x gx dx dx squared plus a n minus 1 integrate a to x dx. So this means we integrate a to x, integrate a to x gx dx dx. So we have dx squared there. Okay, or we can write that and evaluate those things. So we have d n minus 2 y dx n minus 1 minus y n minus 1 a equal to integrate a to x gx dx squared plus a n minus 1 a n minus 1, and then x we evaluate from a to x. Alright, and then we use the condition using condition 2, the second last, that condition here. We have y n minus 1 minus 2a equal to a2. Then we have dn minus 2y dxn minus 2, right, this is 2, sorry, equal to integrate a to x gx dx squared plus a n minus 1 x minus a, this is from that part, and then plus a n minus 2. This comes from the condition 2. Okay, and then we can rewrite this. That gives us dn minus 2 y dx n minus 2. This equal to integrate from a to x gt dt squared plus a n minus 1 x minus a plus a n minus 2. Okay, so what we do here, just change x and t, and again we can write this rewrite that, so you can write dn minus 2 y dx n minus 2. This is equal to integrate a to x, so we have x minus t, okay, gt dx gt dt plus a n minus 1 x minus a plus a2 a n minus 2. So let's call this equation number 7. Okay, and we have 4, and I call this equation number 5. Right, this equation number 5. 4. No, just a minute. I think d and y. This is equation number 6. Sorry, this is equation number 6. 6, and where is equation number 5? 4. Okay, this equation number 4, this equation number 5. Right, so we have those. That's equation number 4 and number 5, and then second derivative, we integrate the second integration, that gives us equation number 6. All right, and this is the equation number 7. This one is equation number 7. All right. Here we use integrate a to x yt dt n means we integrate n times as integrate a to x minus t n minus 1 over n minus 1 yt dt. Okay. Now we integrate 6. Now integrate 6 from a to x. Integrate 6 with respect to x. So we have the x n minus 3 y, the n minus 3y dx n minus 3 from a to x. Okay. Sorry about that. Okay. This equal to integrate a to x gx dx3, okay, plus a n minus 1 integrate a to x minus a dx plus a n minus 2 integrate a to x dx. Okay, then this gives us the n minus 3y dx n minus 3 minus, here we have y n minus 3 a, that equal to integrate a to x gx dx cube plus a n minus 1, we have x minus a squared over 2 a to x plus a n minus 2 x, so a n minus 2 x, we evaluate from a to x. Okay, and then simplify those. So we have the n minus 3y dx n minus 3, that's equal to integrate a to x gx dx3 plus a n minus 1 x minus a squared over 2 plus a n minus 2 x minus a over 1 factorial plus a n minus 3. This equation number 8. And then we use the appropriate condition. Then we have using condition 2 again, appropriately. Then we have the 2, so dn minus 3 y dx n minus 3, this equal to integrate a to x gx dx 3 plus a n minus 1 x minus a squared over 2 plus a n minus 2 x minus a over 1 factorial plus a n minus 3. Got the same. Plus a n minus 3. Okay. This one t. This one t, sorry. That's t. gt dxt. Alright. Now, using integrate a to x yt dt n equal to integrate ax x minus t n minus 1 over x minus 1 factorial yt dt. Okay, so we got dn minus 3y over dx n minus 3. This is equal to integrate a to x x minus t squared over 2 factorial gt dt plus a n minus 1 x minus a squared over 1 factorial plus a n minus 2 x minus a over 1 factorial plus a n minus 3. Let's call this equation number 9. Okay. And if we proceed this, we will end up. So if you look at that from equation number 4, yeah, number 3, 4, 5, 6, 7, 8, and 9. We can see the reduction of the order of differential. All right, from n minus 1, n minus 2, n minus 3, and so on. It will reduce this up to dy dx. Yeah, if you proceed that, it will reduce to up to dy dx, and then on the right side, we again use the appropriate formula that I mentioned earlier. Then we can have a to x x minus t n minus 2 over n minus 2 factorial gt dt plus a n minus 1 x minus a n minus 2 over n minus 2 factorial plus a n minus 2 x minus a n minus 3 over n minus 3 factorial, and so on, up to we have a2 x minus a plus a1. Let's call this equation number 10. Oh, number 10. And again, if we integrate this from x, from a to x, we have, and also we have y equal to integrate a to x x minus t n minus 1 n minus 1 factorial gt dt plus a n minus 1 xa n minus 1 over n minus 1 factorial plus a n minus 2 x minus a n minus 2 over n minus 2 factorial, right, and plus a2 x minus a2 over 2 factorial plus a1 x minus a plus a naught. Let's call this equation number 11. Okay. Now, if you multiply this equation from 3, 5, 7, yeah, multiply equation 3, 5, 7, and 10, and 11 by by C1x, C2x, and 1 C1x, C2x, and so on. C, this is not comma, plus Cn minus 1x, Cnx, respectively, and adding them, okay, multiply each of those, equation 3 with 1, 5 with C1, 7 with C2, and so on, 11 with Cn, and we add them, we arrive at, we have the ny dxn plus C1x dn minus 1y dx n minus 1, and so on, plus Cn minus 1 x dy dx plus Cnx y. This equal to gx plus a n minus 1 c1x plus we have a n minus 2 plus a n minus 1 x minus a c2x plus we have a n minus 3 plus a n minus 2 x minus a plus a n minus 1 x minus a squared over 2 factorial c3 x. Okay, so we can proceed this until we have let's say a naught plus a1 x minus a plus a2 x minus a squared over 2 factorial plus a n minus 1 x minus a n minus 1 n minus 1 factorial cnx. Okay, so you need to look that carefully from the beginning, from the equation 3, and then arrange that. You will get into that expression. Yeah, and last term we have plus integrate from a to x. We have c1x plus c2x x minus t, and so on, cnx x minus t, n minus 1 factorial gt dt. gt dt. Okay, so all this equation, if we take certain representation, can be written as, or we can write this as a phi x equal to gx plus psi x minus integrate from a to x k xt gt dt. Yeah, where we take phi x as that's this part here, okay, it's getting long to write. Yeah, so phi x equal to an minus 1 c1x an minus 1 c1x plus everything inside here, this part here, okay, to the end here. Okay, so just I copy that again, c1 x plus this is a n minus 2 plus a n minus 1 x minus a c2x plus a naught plus a1 x minus a plus a2 x minus a squared over 2 factorial plus an minus 1 x minus a n minus 1 over n minus 1 factorial cnx and that, and our k kernel, this is c1x plus x minus t c2x and so on, plus we have x minus t n minus 1 over n minus 1 factorial cnx. Okay, so you give them this equation number 12, this equation number 13, this equation number 14. Alright, and phi is given by 1. If you look at 1, where is my 1? Yeah, and phi x is defined by equation 1. Okay, so now if you write let us write phi x minus psi x equal to fx. So what we have now, then using then from 12, if you do this into 12, we have 5, bring it 5 to the right side, that left g. So what we have then from 12 we have gx is equal to fx plus integrate a to x kxt gt dt. Okay, so this is the Volterra integral equation of the second kind. Yeah, so this is the Volterra integral equation of the second kind. So from here we can see that the initial value problem, yeah, the differential equation with the initial value problem can be converted into the Volterra integral equation of the second kind by following all those steps. Alright, so I think for this video I stop here. The next video I'll give you example how to do that. Alright, okay, so what we do here, if you recall what we have done, basically we just integrate from the first thing we assign function. Alright, we assign function to the last term dny dxn, and then from then we just integrate step by step until up to we have y terms. Then all those things will lead us to the Volterra integral equation of the second kind. So consider that as a conclusion. So I stop here for this video. Next video I'll give you example on how to do this thing. So bye for now.